Hey everybody, Mr. Quick here. Today we're going to be looking at Eureka Math / Engage New York Math Module 4, Lesson 22, Writing and Evaluating Expressions with Exponents. We've looked at multiplication, addition, we looked at multiplication and addition, we've looked at subtraction, we've looked at all kinds of things. Today we're going to focus on exponents. You're going to write and evaluate formulas involving exponents, so you're going to be given values in real-world problems, and we're going to have to go ahead and solve. Remember, evaluating means to solve. And a couple things, exponents are used in calculations for area and volume, so that's kind of where you would see it in the real world. Some other examples from Eureka Math would be bacterial growth, which we'll talk about a little bit, but those that grows to the power of 2, and compound interest, which you'll learn about soon enough. We won't get into that. Just a quick reminder, exponent, we have a base number and to the power of the exponent. So in this case, the base number is 3 to the power of 5. It is not 3 times 5. 3 times 5 is 15. 3 to the power of 5 would be much larger. What that means is you have your number here, 3, and you're multiplying it by 3. And how many 3's will you end up having? Well, in that problem, it'll be how many, or whatever number your exponent is. So in this case, we have 1, 2, 3, 4, 5. And you have to multiply 5 3's. So that's what that means. So again, we have 3 times 3 is going to give us 9. Times 3 gives us 27. Times 3, let's see, 3 times 20 would be 60. 3 times 7 would be 14, so that gives us 74. Times 3, 70 times 3 would be 210, because 7 times 3 is 21, and this is in the tens place. 4 times 3 is 12, so we'd end up with 222. So anyway, that's just a quick reminder about what exponents are. So let's go ahead and jump into some examples together. All right, example 2. Well, this is our first example. All right, bacterial infection. Bacteria are microscopic single-celled organisms that reproduce in a couple of different ways, one of which is called binary fission. In binary fission, a bacterium increases its size until it is large enough to split into 2 parts that are identical. So it gets bigger and bigger and bigger, and then it breaks into 2 equal parts. Those 2 then grow until they are both large enough to split into 2 individual bacteria. This continues as long as growing conditions are favorable. So like if you have a bacterial infection, it's just going to keep going and going and going until your body's able to kill it off, or until you use some antibiotics or medicine of some sort. So you have this one that grows and it pops into 2. Then this one creates 2, and this one creates 2. Then each of these create 2, and so it gets bigger, and that's what's called exponential growth. It's not just adding 1 every time, it's getting bigger to the power of 2 every single time. So it's getting exponentially bigger, hence exponents. So the first generation would just be this one. Well, this is your origin, I guess. The first generation would be here. So you end up with 2 bacteria. Number of bacteria written as a power of 2. 2 to the power 1, because that means there's just one set of 2. So there's 1, 2 up here. And then you have 2 to the power 1. All right, fair enough, right? So the next generation, then, you're going to end up with 4, right? It doubles. That's 2 to the power of 2. We have 2, and then you have it twice, so 2 times 2 gives us 4. Going to double again to 8. That's 2 to the power of 3. So you see we're increasing our exponent by 1 every time. So 2 to the power of 3, that means I have 3 2's. I'm going to multiply by each other. 2 times 2 is 4, times 2 is 8. There you go. So hopefully you're seeing a pattern in that essentially we're having, every time it's 2 to the power of something. Well, in this case it was 3. That's the third generation. In this case it was 2, second generation, 1, first generation. So in this case it's the 4th generation, so it would be 2 to the power of 4. 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8 times 2 is 16. So we can fill that in. 2, now we're in the 5th generation, 2 to the power of 5 would be 32. And it just keeps getting larger every time down. We're not going to fill this all the way in, but we would have 2 to the power of 6, 2 to the power of 7, 2 to the power of 8, 2 to the power of 9, 2 to the power of 10, and it would just keep going down. So for time purposes, I won't do that, but I just want you to see what we're looking at here. So how many generations would it take until there are over 1 million bacteria present? Well, doing the math there, we ended up with 2 to the power of 20. Okay, because if we ended up doubling it every time, you just have to keep doubling and see how many times you doubled it, right? So that would give us 1,048,576. So, knowing that, under the right growing conditions, this is part C, many bacteria can reproduce every 15 minutes. Under these conditions, how long would it take for one bacterium to reproduce itself more than 1 million into more than 1 million bacteria? Well, if it's every 15 minutes is when you get a new generation, then you'd get a new generation every 20 minutes. So you'd have 20 times 15, 20 15-minute periods. I can do 15 times 2 is going to give me 30. I still have this 0 to bring over for the place value. So I end up with 300 minutes. If I divide that by 60, because there's 60 minutes in an hour, that would give us about 5 hours until there were 1 million bacteria. Write an expression for how many bacteria would be present after G generations. Well, remember, we're doing to the power of 2, and it's to the power of whatever generation it is. So if we don't know what generation it is and they're just telling us the variable is G, it would be 2 to the power of G. Okay, let's look at another example together. This is the volume of a rectangular solid. So here they've given us the height, the length, not the width. This box has the width of W. The height of the box, H, is twice the width. The length of the box, L, is 3 times the width. That is, the width, height, and length of a rectangular prism have a ratio of 1 to 2 to 3. So, if the height is twice, and it's 2, and the length is 3 times, and it's 3, then we have to have 1 W, right? So rectangular solids like this, the volume is calculated by multiplying length times width times height. So in this case, we have 3W times 2W. You can space that out, 3 times 2 times W, right? 3 W's. You end up with 6W cubed. Okay. Knowing this, follow this above example, which is what we just did on the other page, to calculate the volume of these rectangular solids given the width W. They've given us 1, right? So, if they gave us 2, then, I'm going to use a red here. They give us 2, so instead of 1 centimeter, it's 2 centimeters. You're doubling everything because it has to keep the same ratio. So you end up with 2 centimeters times 4 centimeters, because we had 2 before. Before they had 3, so we're going to do 3 times 2, so 6 centimeters. 2 times 4 times 6 centimeters. 2 times 4 is 8. 8 times 6 is 48 centimeters cubed. So, for 3, if we're going from 1 to 3 centimeters, that's times 3. So then 2 times 3 would be times 6. And then 3 times 3 would be times 9. And that would give us 6 times 3 is 18. Times 9 is 162 centimeters cubed. Okay, so I'm going to skip 4. You kind of get the idea, but for the equation here, we have W centimeters, which is whatever they've given us, right? 1, 2, or 3 in this case, times 2 times W centimeters times 3 times W. Whoops. And that's going to equal 6 W cubed centimeters. Hold on. Centimeters cubed. Sorry, my iPad's being a little goofy there. Okay, I know it's fairly complicated. This is a little bit more of a challenging question, but the key is knowing what you have here. If you have these sides, you can fill it in, and as long as you maintain the ratio, so if it's 2 times bigger, 3 times bigger, you continue to increase the length, the width, and the height accordingly, then you're going to get your correct answer. Okay, again, I know that's a little bit confusing. I wanted you to have the example, but we're going to look at more of these together in class and continue to move forward with this. Thank you for watching. We'll talk to you soon.